final piece of this chapter on solutions is going to deal with a set of properties known as colligative properties. So colligative properties are a very special set of properties because these are properties that interestingly depend only on the number or the amount of solute, but not its identity. And so examples of colligative properties are things such as lowering of the vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure. And some of these are things we use every day or at various points in our life, even if we don't recognize that that's what they are. So let's look first at vapor pressure lowering. So in these examples, we are only going to consider cases where the solute doesn't evaporate. Because if the solute starts to evaporate, then that really complicates the situation. So we have something known as Raoult's law, which says that the pressure of any solvent is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So if we have pure water, then Raoult's law doesn't really apply. Because if we have pure water, the mole fraction is 1, and then the vapor pressure of the solvent is just the vapor pressure of the pure solvent. But once we make a solution, so once a solute is added, then the mole fraction of the solvent is less than 1, and it will result in a vapor pressure for that solvent that's less than the vapor pressure of the pure solvent. Now, to understand why this matters, what is boiling point? So the definition of boiling point is when vapor pressure is equal to atmospheric pressure. And so if you think about this now, by making a solution, we lower the vapor pressure of the solvent. And so it will take a longer period of time or a higher temperature to get the vapor pressure to the point where it equals atmospheric pressure. So the result is that because the vapor pressure is lowered by making a solution, as a result, the boiling point will increase. And that's something that we can actually calculate very easily. So we can calculate the change in the boiling point as being equal to Kb. Kb here is known as the molal boiling point elevation constant. It's different for every solvent. We multiply that times I, and I'll define what that is in a moment, times the molality. So I is known as the Van't Hoff factor. So the easiest way to look, the easiest part of the Van't Hoff factor, if we're dealing with a covalent compound, then I alright, that PowerPoint doesn't seem to like what I'm doing right now, so ignore that. So for a covalent compound, I is always equal to 1. But for an ionic compound, I is equal to the number of ions. So sodium chloride, for example, is made up of 1 sodium ion and 1 chlorine ion, so a total of 2 ions. Calcium chloride, 1 calcium ion, 2 chlorine ions, so the Van't Hoff factor is 3. What about sodium phosphate? 3 sodium ions, 1 phosphate ion, I is equal to 4. Alright, so let's look at a sample calculation of this to see where something like this matters. Well, here's one place where this might matter. And let's see if it does matter. So if you were cooking pasta, what's the first thing that some of you do? So many people will often start by adding salt to the water. So why do we do that? Or why might you do that? Well, when you ask a lot of people, they'll tell you that they add salt to the water in order to raise the boiling point. Well, let's see if that makes a difference. So normally when I do this problem in class, this is when I ask the students in class to give me amounts of salt and amounts of water. But I can't do that today. So I've just chosen some amounts. So what is the boiling point of 76 grams of salt dissolved in 3 liters of water? Just to get an idea of what kinds of quantities these are, "76 grams of salt is approximately 4 tablespoons. And then this is a little over 3 quarts of water. So it's about 3.2 quarts of water. So maybe that's more salt than you had, maybe it's less. But these are the amounts we're going to use. Let's see if they make a difference. So in order to do this, we first need to calculate the molality. So the molality, we recall, is the moles of the solute. So that's 76 grams times 1 mole over the molar mass of sodium chloride, 58.5 grams. And we divide that by the mass of the water in kilograms. For water, it's easy. We know 1 liter is 1 kilogram, or I should say 1 gram is 1 milliliter. And so that does extrapolate out to 1 liter is 1 kilogram. So we have 3 liters, we have 3 kilograms. And so we find our water is 0.44 molal. So now we can calculate the change in the boiling point by adding salt. Change in boiling point is equal to 0.51 molal. Oops. I'm sorry. Let's start again. So first we need the KB value, which is we can look that up. It's 0.51 degrees Celsius per molal. We multiply this times the Van Hoff factor, and in water, sodium chloride is made up of 2 ions, so I is 2. And then we multiply this by the molality that we just found, 0.44 molal. And we get a total of 0.44 degrees Celsius. So the new boiling point of the water is going to be 100 degrees Celsius, which is the normal boiling point, plus the change 0.44 to get 100.44 degrees Celsius. So if you think that adding a whole bunch of salt to your pot of boiling water is going to raise the boiling point significantly, turns out it won't. And you'd have to add truly a lot of salt to even get a 1 degree increase in the boiling point. So to get a 1 degree difference in the boiling point, we'd have to add close to 9 tablespoons of salt to our 3 liters of water. When you think about it, that's an awful lot of salt. 9 tablespoons, that's equivalent to what? Over half a cup of salt? So you'd need over half a cup of salt in 3 liters of water to just get a 1 degree increase in the boiling point. So the next time someone tells you that adding salt to your pasta water is going to make a big difference in how it boils and how quickly it boils and what temperature it boils at, well, now you know that it won't actually make any significant difference at all. Right. We can also talk about freezing point. Freezing point is going to have some similar properties and a very similar equation. But where boiling point gets raised, freezing point actually decreases. So what happens is as we add a solute to our pure liquid, it disrupts the way that the crystals are able to pack when the solid forms. And so because that's disrupted, it now takes less energy for something to melt, and that results in a lower freezing point. The most common place that we see this is in the winter. You know, we often in the winter use salt on the roads, and one of the things the salt does is it dissolves in the water and it lowers the freezing point. Now the equation here is pretty straightforward. The change in freezing point is equal to the molal freezing point depression constant. Again, it's a value we have to look up, times the Van Hoff factor, times molality. So the only thing that's different in the freezing point depression equation is we have a different constant. So now let's find what if we add sugar. So let's say we add 100 grams of glucose, C6H12O6, and we dissolve that in 700 grams of water. So again, we can calculate the molality. That's the 100 grams converted to moles. So divide by the molar mass. And divide that by the mass of the solvent, water. So this solution is 0.8 molal. Then we can calculate our change in freezing point as being the molal freezing point constant for water, which is 1.86 degrees Celsius per molal. Again, these are values you look up. Now, what's the Van Hoff factor here? Well, it turns out here it's just 1. Why is it 1? Well, this is not an ionic compound. Glucose is a completely covalent compound, so it won't break apart into multiple ions. And then we can multiply this by the 0.8 molal. And so our change in freezing point here is 1.48 degrees Celsius, which means now our new freezing point is going to be the normal freezing point. Then here we subtract out the change, and we subtract out the change because change goes down. So the new freezing point is negative 1.48 degrees Celsius. Now, this is also a way that we can use to determine the molar mass of an unknown substance. So let's do that. So here we have 17 grams of an unknown compound, and we've dissolved it in 400 grams of chloroform. And then I've given you the normal boiling point as well as the Kb for chloroform. And then the new boiling point was 67 degrees. So we want to know what is the molar mass of the unknown. So the way we would do this experimentally is what we would do is we would take a sample of chloroform that's pure, and we would determine its boiling point. Then we'd take a second sample of chloroform, add some of the unknown to it, and find its boiling point. And then from there, we would be able to do the calculations. So recall the equation we use is delta TB is equal to KB I times molality. Now, which of these do we know? Well, we know the change in boiling point because we went from 61.2 to 67. So that's 5.8 degrees Celsius. KB is given in the problem. All right, the molality is unknown. But what about the Van Hoff factor? If it's an unknown, can we find that? And maybe not to 100% certainty, but it's something we can take a pretty good guess at. Now, why is that? Well, if we're dealing with an organic solvent, it's very unlikely that an ionic compound is going to be able to be dissolved. In fact, for organic solvents, we will almost never have ionic compounds. So we can make the assumption that this is a covalent compound and that the Van Hoff factor is 1. So we can solve for molality now. And we get 1.60 molal. Now remember, what we're trying to find is the molar mass, and the molar mass is grams over moles. We already know the number of grams of the substance. We just need to find moles. And now that we found molality, we know that molality is equal to the number of moles over the kilograms of the solvent. Well, we have 400 grams of chloroform. We can convert that to kilograms. And so we find that X here is 0.64 moles. So what then is the molecular weight? The molecular weight is the number of grams, 17, over the number of moles, which in this case will equal 27 grams per mole. All right, our final colligative property here is osmotic pressure. Osmotic pressure is the ability of solvent molecules, and only solvent molecules, to pass through a membrane. So you might think of something like this. Over here we have water. And over on this side, we have a glucose solution. And here in the middle, we have a membrane that water can go through, but glucose cannot. And so you can calculate the osmotic pressure as being the moles of solute, N, over the volume times RT. And what happens over time is that over time, solvent passes through the membrane and eventually the pressure equalizes and osmosis is able to stop. Now, where is this important? Well, this is most important in cell membranes. So what if your cell is in a high salt solution? Well, at that point, which direction is the water going to go? The water is going to go out. So we're talking about a hypertonic situation, and as a result, the cell shrinks. We can also have the opposite situation, that the cell is in a low salt solution. Now, based on the pressure, the water will flow into the cell. Or we have a hypotonic situation, and as a result, the cell gets larger. So from here, you should work on some practice. This is in class exercise number 17, labeled Colligative Properties.